arbitrary genus, which may be in a kind of word of string theory, should be something like an open topological string or open closed topological string. And I think for many of the string theory physicists, what I'm going to talk is a kind of a classical theorems, which has been established many years ago. But from mathematician's point of view, some of those theorems, classical theorems. I see. Yeah, quantum, but it's old somehow. And many things that I talked is somehow known for a long time. But from the mathematician's point of view, sometimes it is not proper conjecture, because for the mathematical conjectures, you have some equality between something which both sides are well defined. So you need to define to cook up the conjectures. And so somehow what I want to explain is somehow many things are kind of known to physicists or maybe some other mathematicians, but we are kind of slowly going to the proofs, and it takes kind of 10 years for us to make it a conjectures for genus zeros and the boundary component, maybe another 10 years to do it for the higher genus. So we are kind of starting to come to this higher genus things. And so I just want to tell you what is the kind of, at least for me, the present status of mathematical stories on this kind of things. So I want to say a few words about Gromov-Witten theory and open Gromov-Witten theory. So Gromov-Witten theory is something you want to calculate this closed Riemann surface subject so that you have with holomorphic map of homology class, which hits some fixed cycles at the marked points. And what is open closed Gromov-Witten is somehow you have a Lagrangian submanifold in a symplectic manifold, and we count some border Riemann surface and holomorphic map, and which are supposed to hit several cycles in ambient space and some cycles on boundaries, and you count this. So this is the open closed Gromov-Witten theory. And then there is one big difference between usual Gromov-Witten theory and open Gromov-Witten theory. In a usual Gromov-Witten theory, we count numbers which obtain this kind of countings, and these numbers are independent of the choices. And the typical choice is almost complex structures, and you need to perturb the modular space, and or you get a well-defined invariant. But in open Gromov-Witten theory, the numbers we obtain, that kind of counting, is not well defined. It usually changes if you change the almost complex structure, and you change the perturbations, you get different numbers. So that's the kind of main things which I struggle for more than 20 years. And then we obtain numbers, and it's not independent of, but then there is several ways we can proceed. And in some lucky situations, we have some lucky cancellations, so that you can get some numbers which is well defined by several particular combination of the numbers obtained from open Gromov-Witten theory. But this is a kind of more ad hoc, and I don't have so much a kind of very much uniform way to obtain numbers compared to this closed Gromov-Witten theory. In a closed Gromov-Witten theory, you always get a number. But in open Gromov-Witten theory, you are sometimes lucky to get a number, but not always. And what we are working on is first to construct some system of numbers by this kind of not well-defined countings. And those system of numbers will turn out to be a structure constant of some algebraic systems. And this algebraic system is well defined up to some equivalence called homotopy equivalence. And then after we obtain these algebraic systems, we start working on some algebras to get something well defined. It means that you cook up some numbers from these algebraic systems, so that these numbers are kind of invariant of the homotopy theory of these algebraic systems. So this is a bit more kind of systematic, because we first obtain something in a canonical way, and then the process to get a number from this algebraic system is a kind of algebraic story. And so let me, before going to higher genus, let me say a few words what we did in the case of what is done in the case of disks. So that's the simplest case of the count. We count Lagrangian submanifold, we count the number of disks which bounds it. And I think there are several things which is known. In the case of there is S1 actions, and then Melissa Liu many years ago cooked up some invariant. And the other typical case when this Lagrangian submanifold is a real point of certain real structure of projective algebraic variety over real numbers, or at least it's a fixed point of anti-holomorphic involutions on symplectic manifold, then there are several ways to have numbers as a number of holomorphic disks. And in this case, there are what I call lucky cancellations happens in many cases, and we get various ways to get the numbers. There are several people. I'm sorry, this should be A, not E, right? And the other case, if you have a special Lagrangians in which is a Q rational homology pair in Calabi 3-4, then there is a kind of numbers, but this is J-dependent, and there is a wall crossing formulas. And in a case, you have a Tn orbit in toric manifold, and you have this toric Tn orbit has a non-trivial Floer homology. There is some way to cook up numbers. But these as you see, is a kind of ad hoc, so there is not so much a very general stories how numbers obtained. So today I want to discuss something about this, some higher genus analogs. So what I want to talk first is the appropriate algebraic structures we study, and how we can construct such algebraic structures. And finally, I want to mention something how we can get numbers numerically invariant in certain cases. And this numerical invariant should be interesting, but somehow it's still difficult. So this kind of algebraic structures I talked several times, but somehow the stories are kind of made a bit of progress. And I talked something about algebraic structures actually more than 1 year ago. And some part is actually not so much progress, but they kind of go behind, because something which I thought is a theorem is not yet a theorem. And this kind of cook up this kind of algebraic structure is a kind of delicate stories. We need a lot of mathematical works, and we need to use many so-called virtual techniques. And this algebraic stories requires a kind of most sophisticated and delicate case of these virtual techniques. And I am now rather kind of going back to make this virtual techniques more solid, so that we can use it even in this kind of most difficult and delicate case. But anyway, let me explain what is algebraic structures. And this algebraic structures we are working on for a long time with Chilbach and Ratshev, and I believe that we can finish writing papers in the near future. And this, at least we have manuscripts, which should be the final versions now. But and also, this kind of structure is not so much a kind of new. There are many similar structures which are worked out by many people. But the way we cooked up this structure is somehow most close to what we did with Ota Ono in Lagrangian Floer theory. And that somehow fits naturally with this way we cook them up by virtual techniques. But we start with, so let me explain. We start with graded vector space, and we take its symmetric tensor product. And the structures are kind of parameterized by 3 numbers, K, L, G. And you can imagine that these operations are kind of related to this Riemann surface. And this Riemann surface has K income boundary and L outgoing boundaries and some genus. So you have any K, L, G, and you have operations. And we take this K, L, J, and you just put it. So this EKC is just a sum of all this symmetric tensor product, and just extend it to this EC just by doing like this. We pick up any K of, so you have n input, and we take any K of them, and you apply this PKLG, and you just sum it up with this all symmetric group. And the basic equation is this P hat square is 0. P hat is a sum of all of them. And you have some sums, and this H bar and tau is kind of strange. We have 2 origins of this constant. This tau is so-called a string coupling constant. It's Euler number of this Riemann surface, so it's naturally a string coupling constant. So it's well known in string theory community. And this H bar has another origin. And you go back to some version of this stories. You go back to something called a half infinite dimensional formulation of valuation of Hodge theory. It also goes back to 60s. And you go to that areas. You have some constant which appears for that kind of to use this half infinite formalism, and that H is the origin of this H, and that goes back from the long way from random Ginsburg model to come here, and it is used in this simple field theory, the wide algebras, and that is this H. It's not so much physics. I don't know where it related to this Planck constant, but you have 2 different origins. And somehow this looks very similar, but it's slightly different, because this G, K is only on a number of sources, and L has both sources and K and L so has both sources and targets. So they are not completely the same. it seems very likely we can kick out one of them and to have only one formal parameter. But it's a bit subtle, so I just want to keep both of them. So this is the basic equations. And this has contained some various special cases. In case you have only genus 0 and L is 1, L is 1 is only one output and several input, and this equation just boils down to the usual L infinity algebra. And the other case is that you have a genus 0 and you have only one input and only two output. So you have a map from 1 to 2, and this is exactly coincides to co-Lie algebra. It's a kind of co-Lie structures. And if you consider only the case KL is 1, 1, 1, 2, 2, 1, it is so-called involutive by Lie algebra. 1, 1 is a differential involutive algebra. So P0, 1, 1 is differentials. P0, 1, 2 is co-bracket. P0, 2, 1 is bracket. You have three structures. They have some compatibility, which came from this equation P hat is 0. That is called the involutive by Lie algebras. And so we just kind of start from this involutive by Lie and you put somehow all the Phi structures, you get this involutive by Lie infinity structures. So, and if you remember the story about the infinity algebras or L infinity algebras, there are something called a Molar-Cartan element or master equations. And you can do this, and also this Weyl algebras, and also you can do the similar thing for the involutive by Lie algebra structures. You consider this series of element MKL. MKL is a kind of case, in a case symmetric powers, and you take this for each G, and you take this infinite sums, and you take exponential. Exponential you can just plug in formally, and addict topology it converges. If you apply P hat, you get these equations. And this is a kind of master equations for this involutive by Lie infinite algebras. And what's good for this master equation is once you have this element M which satisfies this master equation, you can twist this originally P hat using this master equation to obtain P hat M. You get the twisted involutive by Lie infinite structures. So usually if you have a kind of if you have a differential graded algebras, you have an element which is dm plus mm is 0. It's Molar-Cartan element. You can regard M as a flat connections. You get another DGA. The story is very much similar, but it's a kind of more involved. That's the story about this Molar-Cartan element. And so I just want to explain summary of the story of this higher genus Lagrangian Floer theory. So we take this we first take this, are there any, it's this, right? This one? How? This one. Does it work? It looks? No, okay. I can just do it like this. So we take this free loop space. Okay. You can take this free loop space, and for any manifold, we take S1 equivalent homology of free loop space relative to the constant loops. You get this groups, and this Dennis Sullivan and Moira Chas's string topology gives here. Yeah. Can be generalized that this contains involutive by Lie infinity structures. I don't know how much this is established. At least in a homology level, it gives involutive by Lie algebra. At this stage, it's established. And here you go to this infinite things, including chain levels. Probably the transversality issue is still kind of not yet completely well written. So there might be some subtle thing. But this involutive by Lie infinity structure is something we use. Then, if this L is happen to be a Lagrangian submanifold in a symplectic manifold, we get some series of elements which satisfies this master equations. And this MKG beta is actually this invariant which is related to holomorphic curve. So what I want to explain today is a relation of this story to perturbative Chern-Simon invariant, and also a way to obtain enumerative invariant. And unfortunately, what I'm going to talk here is a bit is not the part which is a kind of I can write down the rigorous proof. And as I said, that the last slide, what I wrote in this last slide, I can start writing the rigorous proof. Unfortunately, I didn't do it yet. But this next slide, there are several problems because of which I cannot write down the rigorous proof. And I want to explain what is the problem also at the same time for the mathematical rigorous argument. So first problem is we need to replace. And so to get this chance, to get something related to Chern-Simon invariant and to enumerative invariant, we need to replace this relative homology to the homology of loop space itself. Because usually the enumerative invariant lies in H0 of this, that's just related to the point class, and this H0 disappears if you just consider this relative invariant. But I want to explain it in algebraic terminology, because that's necessary. And but to explain this, so this is also known to the string topology community. If you want to replace this relative homology by this absolute homology of the free loop space, S1 equivalent homology of the free loop space, and you want to define this co-bracket, that is a kind of something which is related to this genus zero Riemann surface with no input and one input and two output, then there is a problem to define this co-bracket, and that's known to also to many people, but let me explain this point. So how this co-bracket is defined? So we consider this cycle in a free loop space. So this is S1 equivalent homology. So let me pretend that this action is free. Then this homology class is just a cycle on this quotient space. Then we consider this set or this parameter space of the cycle plus two elements on a S1, so that so gamma A is a loop represented by this parameter set. T goes to gamma A of S, so you consider this kind of figure 8 where this self-intersection exists. So this is a submanifold of this R cross S1 cross S1, and this is actually the cycle which represents this delta, because you consider this cycle, then you have a pair of loops. One is this loop and the other is this loop, and you get this element here. You have a map here, so you have a kind of element in the product of loop space and with itself, and then you have this cycle gives an element here. This is basically this just Sullivan's idea to define co-bracket.
Are you allowing S equals T?
Pardon?
Are you allowing S equals T?
Yeah, that's a trouble. So I want to say that what Dominic tried to mention. So if you want to study this boundary of alpha, it has some one codimension 1 component. It gives in a following way. So you have this kind of self-intersection things, but this self-intersection point may kind of, so if you move on this point, this self-intersection point moves like this, and finally it ends up with this thing. It's exactly the case when S is equal to T, and this is a codimension, this is the codimension 1 phenomenon. So if you see carefully, this boundary of R may not be a cycle because of this phenomenon. But then if you think a bit, then you can get rid of this codimension 1 boundary if you consider kind of free loop space relative to constant loop, because this one corresponds to the pair of loops like this, and you go further. So this part gets to the constant loops. So that is something you model out. So if you model out constant loops, you don't have to worry about this bad boundaries, and then you can get this operator here. So in place of this operator, you have this operator, which is omega L relative to L. L consists of this free loop, just the constant loops. So you have this operation at least in the level of homologies, rather kind of simply by these reasons. But this problem is a kind of serious problem. Somehow people in string topology struggle with this kind of problem, including ourselves. So we can avoid by taking relative cohomology with constant loops. And then so this I just explain in a geometric language using this string topology. But you can realize this problem if you do it in a purely algebraic ways. So let me consider this cyclic bar complex. It's a kind of k-tensor product of this drum complex divided by the cyclic group actions with signs. And this cyclic bar complex, and you just take this in place of drum cohomology, you have cyclic bar complex. And this boundary operator D and this bracket is a wedge product. This wedge product on this drum complex, this altogether defines a boundary operator on the cyclic bar complex. It gives a cohomology. And the point which is rather important here is this K. The number of this tensor product is start from 1, not from 0. Usually in a bar complex, you start from 0 tensor, it's a ground ring, but you need to take this from k to 1. And then if you start from k equals 0, probably this is likely to give a S1 equivalent homology of the loop space itself. But you remove this the point when k is 0, then you lose this certain part of this information of the free loop space, and you get something similar to this S1 equivalent relative homology. Not exactly, I think, but this is one point. So now there is a kind of several step. We need to cook up this invariant. So since this transversality issue in string topology is not so easy, so we want to kind of use this drum versions and cyclic homology of drum complex in place of loop space homology itself. So it's algebraic analog of this string topology. Then we take this cyclic bar complex and cyclic bar complex homologies. And we use this D and the Poincare duality only, not wedge product, by introducing involutive by D structures. So the differentials and the bracket and the co-bracket on this. Co-bracket I already explained is related to this self-intersections, and the bracket is related to two loops which intersects one point. And this bracket and the co-bracket are both defined by, let's see, it is this picture. So this is a definition of the bracket, and this is a definition of co-bracket. I'm sorry this looks so much similar picture, but this left-hand side you have two different loops which meet at one point, and the right-hand side it is a single loop which has self-intersections. And this first one is a bracket, and second one is a co-bracket. And this intersection theory on this drum complex is just related to Poincare duality. So you use Poincare duality to define bracket and co-bracket. You have algebraic formulas to do so. I don't want to write down, but intersection theory on L gives this bracket and co-bracket, and you have D on this. And then the first part of the story is that you have these things. And the second part of the story is that you have kind of a boundary operator. It gives the solution of master equation involutive by the algebra structures on this. And if you try to do this in a case of this, in case you include k is 0, then actually you cannot do it. And I don't want to explain the reason, but the reason is actually there is a general statement. You have a cyclic DGA, and then you take this cyclic bar complex which starts from k equal 1, then always product structure gives this solution of master equations. And if you have a similar thing for infinity algebras, cyclic infinity algebras, then even if you remove k to 0, you cannot get solution of master equations. You get a solution of Molar-Cartan equations if you forget this co-bracket. But if you want to include co-bracket, you will be in trouble, actually. So, but fortunately, if you have only bracket, it's okay. The reason is, not so much. Yeah, maybe I don't want to talk about it. But the reason is, if you have this circle intersections, and you have only 3 marked points, then there is no marked points remain here, so it is something which you erase. And you have something here, it's 4 marked points, and this one remains, then this gives some bad effect. You have to go to a higher loop. But that's the reason. But anyway, so if you just exclude this k equals 0, you get this problem 2 is okay. And this problem seems to be somehow related to this algebraic version of this problem about string topology. So now I want to go to the third point. So there is general procedure. There exists a homotopy equivalence from this cyclic bar complex to this cyclic bar complex of the homology. So here cyclic bar complex of the drum complex. This is cyclic bar complex of drum homology. There is a kind of homotopy equivalence between them. Here we put this IBL structures induced only by Poincare duality. And I want to explain this third point because actually the proof of this third point is related to this perturbative Chern-Simon theory. So to prove this, you need something very similar to the perturbative Chern-Simon theory. And if you can join this to this actual perturbative Chern-Simon theory, probably you can include this enumerative invariant. So let me say a few words about this perturbative Chern-Simon invariant. We have a 3-manifold with flat bundles, L and E. And usually we assume homology is 0 to have a well-defined theory. And then we get some, so then the perturbative Chern-Simon theory, so let me review. In the perturbative Chern-Simon theory, we have this 3-manifold with flat bundle with 0 cohomologies. And you consider some kind of enumerative, so we get some enumerative invariant, perturbative Chern-Simon invariant, by studying or some kind of integrations of a metric ribbon graph with some integrals. And to get this integrals, you associate each edge a propagator G. Propagator G is some kind of chain homotopy from 1 to 0. So here we use this conditions that this homology is 0. And then for each interior vertex, so this is a trivalent. I'm sorry, this is trivalent metric ribbon graph. Trivalent, right? So for this trivalent graph, we associate this triple product. So you have 3 differential forms. You just take product and integrate. So this is, I'm sorry, I don't want to, I cannot go more detail, but somehow you using a sum over this metric ribbon, trivalent metric ribbon graph, and put propagator to each edge and this triplet integral on each vertex, you get this invariant of perturbative Chern-Simon theory. So this is perturbative Chern-Simon theory. And if you want to try to cook up this homotopy equivalence from here to here, we do something similar. So let me consider the case when we put, so here we put this exponential of wedge. So wedge is a solution of master equation of this IBM infinity structure. So it's an element here. It's dual to this cyclic complex. It's actually this one. And they have a kind of dual to this cyclic bar complex of the round complex. And then we take its exponential. So it's an element here. And then we should get element here. And we get some count. And what should we get? So you just transform this exponential by this homotopy equivalence. We should get an element which is a homomorphism from this many tensor product of cyclic bar complex of the homology to real number. It's an element of, it's a dual of the element of this E of this bar complex. And to obtain this, we proceed in the following way. We have this H's. H are element of the Ram cohomology. So we have this kind of M1 element is the Ram cohomology and MK element of the Ram cohomology. You take this tensor product. And what we need to do is just we have this input and we need to get a number. That is something what this homotopy equivalence is required. And we define this number by very similar integrations of a metric ribbon graph. What is different here is the following things. In the case of perturbative Chern-Simons, we have only interior edge and interior vertex. Interior edge is just a line, and interior vertex it is trivalent. But then here we have also kind of exterior vertex and exterior edge. Exterior vertex has only one edge. Exterior vertex is, so this is exterior vertex, and this edge which came from exterior vertex called exterior edge. Then we do very similar integration and sum. To integrate a vertex, you put this propagator. I'm sorry, this is wrong. This is not 1. This is 1 minus harmonic projections. In our situations, we have this non-trivial homology. So 1 minus harmonic projection is a kind of is homotopic to 0, and your propagator is exactly this G. So this is 1 minus harmonic projections. And this interior vertex is associated with the same thing here, and it is actually this lambda, regarded as a kind of cyclic bar complex. And for the exterior vertex, you associate these differential forms. It's harmonic forms. And then exterior edge is just identity map of harmonic projections. So for each ribbon graph, each vertex you put this guy, and each vertex you put this, and for interior edge you put propagator G, and you do the very similar integrations, you get a number. And that number actually is obtained by this one. So for each genus, for each genus and for each kind of choices of H's, you take integration and sum, you get a number. And in total, you get this element. And that is actually satisfies this master equations. So that is what we obtain from this business. Then so let me explain what is this. So let me recall perturbative Chern-Simon, you don't have any exterior edges, basically because you don't have any homologies, right? There is nothing to put as the exterior vertex. It's 0. And in the case of this, so this is the kind of things which I want to write here. So we consider 2 cases. One is a case you start from case 1 of this cyclic bar complex, and the other case you want to include case 0. And here we restrict the case of this homology is 0, And here we include the case the homology is non-zero. And in perturbative Chern-Simons theory, we can include this zero, and you have but you assume that the homology is zero. So actually, in this case, only case zero remains, right? I mean, if you have only at least one factors on a homology, you get zero. But the tensor product of zero tensor product of trivial vector space is a ground ring. So what you end up with a number, and this number is actually invariant perturbative Chern-Simons theory. And the other case, we have this case when homology is zero, but I need to exclude that case zero. Then we got this homotopy equivalence from the IBL algebra of cyclic Bar complex of drum complex to the IBL infinite algebras from the cyclic Bar complex of drum cohomology. So this one and this one can be calculated by basically the same integrations using propagators and trivalent vertex. But they kind of work in different places. And something I still cannot cook up in completely rigorously is this part. I want to include the case homology is non-zero and include case zero. This should be a mixture of perturbative Chern-Simons invariant and homotopy equivalence. And I don't know any appropriate algebraic language to describe this. And I think after this perturbative Chern-Simons theory was discovered, it seems already mostly 15 or 20 years. And then they start from the case when this homology is zero. And there are several attempts to generalize it to the case homology is non-zero. And I think people, at least the mathematicians, are not so much successful to find a very good story about it. Here, I think I heard a few talks by Axelrod, who gave a talk about it. And I don't understand it. And unfortunately, Axelrod do not continue mathematics or physics. So I don't know if there is any rigorous theory here to join this. And the story is rather subtle. And if we know what happens here, I feel that should be the way we get enumerative invariant from this Lagrangian Floer theory. So this is one story. So the constant maps part. So what I want to say is that so this story, you have a Lagrangian submanifold, and you just count the number of constant maps from both the Riemann surface, which is a holomorphic map, of course, and which is homologous to zero. Then in the case of homologous to zero, you don't have any holomorphic map other than constant maps. So you count the constant maps from the both on the Riemann surface to Lagrangian submanifold. This is a highly non-transversal problem. So you have to some way to cook up some system of numbers in natural ways. And in these two cases, they should give this map or this guy. And I don't know what have to come here. And you can get here, you get somehow. At least constant map part of the full story of Lagrangian Floer theory. But I think the basic problem is how I don't know how to handle this. But since even I cannot do it, there are some ideas. So the problem is, the idea is to use Fulton-MacPherson compactifications of configuration spaces. The reason we might use this kind of thing is the following things. If you want to see the relation between loop space and this cyclic Bar complex, what we do is to put several marked points on a S1, and you approximate loop by you approximate loops. I mean, it's a kind of Shen's idea. You approximate the drum complex of loop space as a kind of tensor product of the drum complex of original manifold. What else you put several marked points on the loops. And then the problem here is a kind of you take several marked points on the loops, but two of the marked points just collide, as this Dominic mentioned. So usually it gives this drum differentials. But if you want to use this with a moduli space, then you need to study moduli space of both the Riemann surface together with several marked points. And the problem is when these two marked points collide, and that is the point where this kind of modular space gets very singular. And you want to kind of make everything smooth. Not only that, you have to make all the evaluation map to the Lagrangian submanifold to be submersions by somehow using this. But of course, if this collide, it's kind of ridiculous to make it submersion because these two map points should go to the same point. So you have to go to the evaluation map should not go to the kind of direct product of Lagrangian submanifold. It should be some kind of configuration space of Lagrangian submanifold. And the point to collide, there is something called Fulton-MacPherson compactifications. So you have to use Fulton-MacPherson compactifications. In the point in a boundary value, two marked points collide. Then you have only one point, but you have to also remember the first derivative of this loops. So in the case we have just two marked points collide, you can just consider the point, 1 point plus its tangent space. But you have several things, you have to use the tangent space in more sophisticated ways. And to make this all kind of compatible, and also you want to prove, you want to show that this evaluation map at marked point on boundary should be a map to this certain kind of Fulton-MacPherson compactification, so that it is stratwise submergence. And I believe if one can do it, we can resolve this problem, but it's far away. It's still.
So you mean Fulton-MacPherson of Lagrangian?
Yes. But it's still a long way for me to go. But so now, so if one can do it, then somehow, you know, this is the usual thing. But you have to not only count this, but also count this. And we have this, and two marked points are kind of joined by propagator. And you include not only this, but all of this kind of things. So this usually should be regarded to genus 2, but you have this propagator, this should be regarded to genus 3. So this one together with this and with other similar things should give this count, and that is actually this. So this is actually, so you consider from this part, then for this part, you have only a count. So yeah, so this kind of count, you have a Lagrangian submanifold, you have a kind of holomorphic curve with boundaries. Then you got this, you got an element of cyclic Barr complex here, and you apply pi, you get element here, and that is somehow counting this kind of things also. And you include, in the case of case 0, then you finally get a kind of enumerative invariant. So that is something which should be a kind of perturbative Chern-Simons invariant together with its kind of quantum effect. That should be the invariant which we should cook up. But unfortunately, I cannot do it yet because of this problem. But so this is the first problems. And the second problem is, but this still depends on your almost complex structures. I mean, let me suppose that I can do everything like this. But still, we need to see whether it's J invariant. And actually, it is very likely we have to get the invariant of the perturbations. So it's something already something non-trivial. But still, if you change your almost complex structure, you get something dependent on J. So it's not yet good enough. And this problem of J dependence has already appeared. So if you change this almost complex structures, this kind of things appears. And this already related to this genus 0, so let me explain it. And actually, this problem is related to some confold transition type things. So the problem, as I said, appeared already in the genus 0 case, and this is observed by Melissa Liu and also Otaona and myself independently, and several other people probably. It is a similar thing. So you consider this Lagrangian submanifold, and in a Lagrangian Floer theory, we count disks, and together with marked points, at least one marked point is the boundary, and it gives a structure. But if you want to get enumerative invariant, you have to study the case when you have no boundary marked points to count this. And then there is similar famous wall crossing phenomenon. So if you change this J, then this boundary curve became just a point here by S2, which intersects with L. And this occurs in condimension 1. It's a boundary. So if you just count a thing like this, then when this happens, then you get a different numbers, so you don't have a well-defined things. And typically, in the case of Calabi-Yau manifold, then this occurs in condimension 1 because L is 3 dimensions, this is 2 dimensions. So if you move J generically, this sphere moves in a random way. So in the condimension 1, it hits your Lagrangian submanifold. And at that very moment, you have this bifurcation, so this counting invariant is not well defined. So this is a kind of basic problems to have a invariant in the case of these countings. And in the case of disks, there are several ways. So in the case of Calabi-Yau 3-fold special Lagrangian, this occurs in the kind of, and this condimension 1 phenomenon, and we can, there are several ways to kind of take care of these problems. One is to restrict the case where the boundary curve is not homologous to 0. Then you cannot observe this phenomenon because the boundary curve S1 will not shrink to a point. And I think this is basically the case. In some case, this Walsher is taken because he takes something which is odd degree, and this implies that RPn and RP3 and odd degree, then the boundary is non-trivial. So this doesn't occur. And the other thing is that we just live with this by proving some wall crossing formulas. And the third thing is to assume that L is real and use some cancellations in a modular space with S2 with symmetry of fixed point free orientations. This is, I think, a few weeks ago I had a talk with Tefrani, and Zing and Tefrani is going through this argument. But I want to explain some different ways, and this is, I think, not my ideas, and I think I first heard it from Dominic Joyce, but maybe somebody else also knows about it. So we consider the case when the fundamental class of your Lagrangian submanifold is 0 on H2 of X. Let me restrict the case when can be a threefold under special Lagrangians. And then we take 4 chains N which bounds L. So then we consider this one, not only this one, but also this S2, which with one marked point which is N. So you take this together with this. And this has the same virtual dimensions. And you see the situations when this L, so when this curve shrinks to the point, you see exactly this configurations, which lies on the boundary of N. That's L. So if you just count this guy with this guy, then this bad wall crossing just cancel out, you get very fine numbers. So this is the ideas. So in a case when you have a Lagrangian submanifold together with a 4 chain which bounds L, then all together it gives a good, very defined invariant, which should be independent on J. That's the idea. And this idea you can take also in a higher genus case. So suppose you have a L, which is a kind of boundary of N. So as I said, that we first count L, but then we'll be in a trouble when this boundary loop shrinks to a point at some very moment of J. But then we include this, this one shrinks, then you have to include this point fits to N. So when this point happen to be on L, then this happen to go to the shrinks to point. So this guy together with this guy cancel that bad phenomenon. And this guy, but again this one may shrink point, so this is include to this guy. So for each, so you have either loops which bounds on L or marked points which hit on M. So you just count all of them, you can cancel this. Of course, you have to those include this G, somehow something like split several disks which is connected by this propagators. So this part I think one can make rigorous, provided we have this kind of business of this problem string topology worked out. So together with this ideas on another case, then we get somehow get some invariant which is independent on J. So now let us like this kind of invariant like this. So you kind of L and N. So in place of here, so this looks something like Gromov-Witten, but you have a one boundary component, which is either a boundary component which lies on L or marked point which is on N. And N is not a cycle. It has a boundary. Its boundary is N. So you got this. So you can say that this pair of L and N looks very much similar as a cycle on an ambient symplectic manifold. You either have a Lagrangian plus boundaries or a cycle. And you can guess the Gromov-Witten story in the same way. And then something conjecture is this. This guy is conjecture to be related to this conipolar transitions. So you have a X prime which contains P1. And then this P1 gets singular. They have a Lagrangian S3 which is X. So this is called conipolar transitions. And then we take this N prime. So this N prime is a Poincare dual class of this P1. So by this change, this N prime dies, right? Your second batch number became 1 less. But then this N prime corresponds to this N here. It's a 4 cycle which bound S3. So this N prime dies, but you get this N instead. And so the natural thing. But let me mention here that there is a work by Ivan Smith, Richard Thomas, and S.T. Yao. When X is symplectic with 3 Lagrangian submanifold, then this S3 is homologous to 0, if and only if this S3 is so if S3 can be a Lagrangian, if and only if. Is correct? Yeah. I mean, you can deform this conipolar transition in the symplectic way only in case this S is homologous to 0. And this is not only the case as this S3 is connected. You have several conipolar things right at the same time. You resolve it. Then you can resolve it in a way so that it still keep this symplectic form, so that all are Lagrangians, if and only if the sum of those cycles are 0. So you can do this similar business in the same way. But for simplicity, let me do this. And then the natural question is that whether this equality is true. So something you want to do is just before on X you have this kind of Gromov-Witten invariant, and I want to compare this Gromov-Witten invariant of X. But the problem is you don't have enough cycles because some of the H2 class in X prime dies when you go to X. But in place, you have this pair of L and M. L is S3, and N is a kind of canonical Paul cycle which bounds it. And you may ask whether this is true. And this is also not ideal. As Dominic mentioned also something. And then actually, I think there is a paper by Teflani also, this paper. I think one can use this paper and everything has worked out in mathematical rigorous way. I think one can prove it, provided alpha is non-zero. The main, I'll go back, but the main argument is the following thing. So as I say that the count is, we count this L together with this, so in a simplest case, we count this disk together with this pair with this, which fit N here, right? Then what this Teflani's paper observed is that in the case when L is S3, and when S3 shrinks to a point, in the limit L shrinks to a point, then this count is actually 0 in a limit. There is no such a disk. So you can imagine when N is smaller and smaller, then this kind of configuration is very hard to realize, and you can find some kind of analytic argument to avoid it. Actually, it's rather strange because this is a kind of main part, this is a kind of collection term, but in the limit, when this Lagrangian submanifold goes to a point, your main term just goes to 0, you have only a collection term. But this collection term, of course, is equal to this Gromov-Witten invariant when N is replaced by N prime. And this is naturally became 0 because if you go to the, after coniform transition, you have this only P1, and this by just dimension counting, this P1 does not likely to intersect with other holomorphic spheres. So this one should die and only this one remains. And this one should survive by this coniform transition because this happens away from this singular point. So, so this should prove this equality. But I don't claim I prove it because I cannot define the right-hand side. So something which I cannot define, I cannot prove any equality. But as far as we can prove this constantly, this invariant, this equality is very likely to be proved. And it is famous about that. In the case alpha is 0, this argument breaks down because in the case of alpha is 0, it's a kind of a constant map to this Lagrangian S3. And this correction term looks very much, the main term very much like untransversals. It goes to infinity. Everything goes to infinity, so this argument breaks down. So we cannot prove the case when alpha is 0, but if alpha is 0 is case very famous things. It's a kind of perturbative Chern-Simons Y3 is equal to multiple cover count of P1 in Calabi-Yau threefold. And this is, of course, a very famous result of Koppa-Huma buffer. So in a case when alpha is non-zero, probably one can go this analytic argument. When alpha is 0, we can use this classical result. So that should be the proof. But actually, I don't like this proof of using this so much. So problem is, it is also possible to prove this result on alpha equals 0 using analysis or geometry. I mean, you want to count some maps to the S3 with highly non-trivial things, and you go back, you have a multiple cover count of P1. And I think the proof of this famous Koppa-Huma buffer count them separately. On one side, they use conformal field theory, and on the other side, they use fixed point localizations to them. It's miraculously match, and this miracle I like very much. But somehow it's a miracle, so there's not explanations. So something I want to do is just to understand it, but then to understand it, probably one can try to do it more analytically. But I don't have any ideas how to do it. Actually, I have this problem for more than 5 years. I never succeeded to cook up any reasonable ideas to prove it more geometrically. And so maybe so I'm almost finished. I just say a few words what one can expect more. So we may include, so here we just consider one Lagrangian submanifold. So we may include the case when you have two Lagrangian submanifold. Then the role of this homology group of L is played by this Floer homology between two Lagrangian submanifold. And then there should be something like a Q-deformed perturbative Chern-Simons type invariant on these pairs. And in a particular case, when L1 and L2 intersect on S1, and L1 is S3 and it's a knot, then this guy is a kind of Q-perturbative version of knot invariant. This kind of things is now kind of discussed by Oguri Buffer and now many people recently. But this I don't yet so much study. And the last thing I want to say is that if you have SYZ fibrations, and we Calabi-Yau threefold, then for each fibers, we have this invariant of this solution of this master equation. So you can try to do the family versions. Then it seems very likely that you can give a kind of quantum container Spencer theory of BC of V. And so somehow what I expect is that so you have this. Then once the homological mirror symmetry will be established by using family Floer homologies, then the story of this Kelvin-Costello somehow completed using this BC of V mathematical rigorous way looks very much similar algebraic and geometric kind of framework which I explained here. So it seems very likely we can include these higher genus versions to prove BCOB using family of Floer homologies in this justified relations. But this is not so much. This is the kind of most ambitious part of the stories. So my hope is that what I talked here is a kind of not so many things yet, but somehow we are now. I am trying to move from genus 0 to higher genus, and then maybe another 10 years, maybe we can just prove everything. That's I hope. Okay, thank you very much. Yeah. Mm-hmm. Kataneo Maniavich? They did it?
They did, yeah. They didn't use the language of cyclical homology, they used the language of the alpha cooking. You can kind of translate back and forth.
Okay, so I have to see it. Thank you very much for the remark.
Do you have any kind of version of the Lagrangian Floer homology involving high genus curves?
So this is the kind of as a homology group, I don't know. Because somehow the problem is you have several, I mean, if you go to higher genus, then you cannot kind of restrict the case boundaries connected. So you have several boundaries, so I don't know how to match it in a higher genus into this boundary operator. So, I mean, that should be interesting problems. But yeah, I just want to, if I want to apply this kind of thing to simplex topology, then I need to answer your question, but I cannot.